In this exercise, we'll put rotational kinematics and rotational dynamics together, much like we've done with linear dynamics and linear kinematics before. So what we're given here is a merry-go-round and a child pushing on it with some force. So we have there's a merry-go-round here, and then a child pushes on it with a 25 Newton force, like this. And we're given some dimensions and some information about this. This merry-go-round has a radius of 4.4 meters, has a rotational inertia of an axis about its center, so an axis which goes through right here, a vertical axis, so imagine this is going into and out of the screen here. So the rotational inertia of the merry-go-round about that axis is 245 kilogram meter squared. And remember, you might say, oh, this looks kind of like a disc, but a merry-go-round has like these handles on it out here and all this stuff, and so we can't actually say that this is going to be modeled as a uniform disc or a hoop or anything like that. This is just, this shape has this particular rotational inertia. So don't try to infer from here that this is equal to like 1/2 mr squared or anything like that, because we can't really infer that. We don't know. We're not told anywhere in here that this merry-go-round is a shape of a circular disc. So we can't do that. We just have to use its rotational inertia as it is this way. We're also told, it starts from rest, right? It says, if the merry-go-round is initially at rest, so omega naught is equal to 0. And the kid pushes on it for a time of 20 seconds. So delta t is 20 seconds here. And what we're looking for is we're looking for how fast is it rotating after this 20 seconds. So for part A here, we'll find part A. We're looking for the rotational velocity after 20 seconds. So I'll call this omega 20. Rotational velocity after 20 seconds. B, we're looking for how much work was done. So the work done by the child on the merry-go-round. So work by child on merry-go-round, MGR. And lastly, the power, right? So the power supplied by the child. So these are the things that we're looking for, and we'll do them very much the way that we would linear quantities as well. So let's start out with part A. So the solution to A here. So we want to know how fast it's moving after 20 seconds, and we know the time, right? And we know the starting velocity, and so you might say, all right, I know omega naught, we want omega final, we know the time. If we only had a fourth thing, we could solve this. And there's only two other things we could put in here. We could either put in a delta theta, or we could put in an alpha, right? And then we could choose different kinematics for it. But I would think it might be easier, or easiest, to recognize we're also given some information about force, right? We're given a force over here, and also a mass distribution, right? And actually how far away that force is applied. If it's a 4.4 meter radius, then that means that this push is 4.4 meters away from the axis of rotation. Therefore, we can get a torque with these, right? There's our torque. And therefore, we can get a rotational acceleration. And so what the most straightforward way to go about it, and there are other ways to go about it, we can use omega equals omega naught plus alpha t, right? Where this is going to be omega 20, and this is 20 seconds. And this alpha will be the net torque divided by the rotational inertia, right? Because this comes from torque equals I alpha. Newton's second law for rotation. So we find our net torque. The net torque acting on it. And this is, frictionless and all that. If we had friction here, we could just subtract that frictional torque. So the net torque is the 25 newtons times the radius, 4.4 meters. And, this is, we have to, note here that the child pushes tangentially to the edge of the merry-go-round. So as the merry-go-round goes around, the kid continues to push tangentially, right? So pushing here and then pushing like that, pushing like that. Otherwise, we would have to, change our force there. But the kids, and it makes sense, right? That the kid would always be pushing tangentially because they run around with it, right? Or he or she runs around with it. So that's the net torque. And then we have, I'll go ahead and find our acceleration. So the net torque divided by I, and I was 245 kilogram meters squared. And so this is equal to our alpha, right? And alpha comes out to be 0.45 radians per second squared. And so then we can take this and plug it into kinematics up here. And we have the angular velocity after 20 seconds, omega 20 is equal to, it started out at rest, 0 plus 0.45 times 20, and this is equal to, this is 0.45 radians per second squared in 20 seconds, so we'll end up with radians per second, and it's 9 radians per second. This is how fast it would be rotating, this rotational velocity, after 20 seconds of pushing with a constant force. Okay, this is part A. Now for part B, we can find the torque, or actually, sorry, was the work, right? So remember, work is parallel force times displacement, right? This is for a linear work. And so rotational work is basically the same thing. This is linear. And when we go look at rotational, it's just, we're going to take the force and we rotate it by our rotational force, which is torque. And instead of a linear displacement, we'll look at it with an angular displacement, right? And these are, vector quantities as well, so our rotational work can be positive or negative, right? Rotational friction would always be negative, right? It'll always oppose the motion, etc. So all the same things hold true there. And so we see here for rotational work, this is equal to tau delta theta, torque times angular displacement. And this torque, of course, is force, perpendicular force times the moment arm, right? And so we actually see here the rotational work is perpendicular force times the moment arm, which actually in our case here is the radius, times delta theta, right? So we have this and this, we just need delta theta, which we could actually get from kinematics as well, right? Now that we have an alpha, we could find delta theta. And so we can get delta theta equals omega naught t plus 1/2 alpha t squared from kinematics. It starts out at rest, so that's not so bad. And delta theta is 1/2 of 0.45 times 20 squared, and then delta theta comes out to 90 radians. And then the work done by the child is the force radius delta theta. It was 25 newtons. times 4.4 meters times 90 radians. And you see here, radians are actually unitless, right? So we have Newton meters, so we have joules. And the work done, this comes out to 9.9 times 10 to the third joules. Or we can say here, this is equal to 9.9 kilojoules, if we wanted to, of work. So the child does 9,900 joules of work. And this is part B. And now for part C, the definition of power for rotation is the same as the definition of power for linear. Power is defined, and this is a capital P, not to be confused with a lowercase p for, remember, linear momentum. This was a lowercase p, which is a vector. This is a uppercase P, not a vector. This is power. P is equal to power. And this is, power is just the rate at which work is done, or the rate at which energy is consumed. So the rate that a light bulb consumes electrical power is, the rate at which a light bulb consumes electrical energy is the power rating of the light bulb, or the rate at which a power plant makes energy, or really converts it to electrical energy, is the power that is generated by that power plant. And so this is just work per time, or the change in work over a time interval, the work done per time. And so if it took 20 seconds to make 9,900 joules, then the power is equal to 9.9 times 10 to the third joules divided by 20 seconds, and this power is equal to 495 joules per second. And this joule per second is a very, very common unit. It is called a watt, which we symbolize with a W, not to be confused with the W that we use for work, right? So basically, if it's W equals something, this is work, and if it's something equals blah 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 W, this is watts, right? So careful where that is. So this is watts. So the power that the kid is exerting onto the merry-go-round is 495 watts. So basically, if we have like incandescent light bulbs, like 100-watt incandescent light bulbs, and kind of the old style, a lot of light bulbs are going to CFLs and LEDs and whatnot, then the kid could power 5 light bulbs while he pushes on the merry-go-round like this. If he slows down at all, then the lights are going to get dim. So unless you use light bulbs with the lower wattage consumes less per energy. So if you can get like light bulbs that maybe they have the light equivalent of a 100-watt light bulb, but they only use like 15 watts, then you're only using like maybe an eighth of the or a seventh of the energy per second that you would normally. So watts are actually joules per second. So it adds up very, very quickly, actually.